Hello guys, today's lesson is about the static friction. In this video we will learn it all. Okay, let's start with a very easy and simple experiment. There is a box and I promise the box to be all at rest during my experiment. If it is at rest, the net force acting on that is zero. Suppose that I pull the object with a force of 3 newtons rightward. This 3 newton of force will have an opposition against it because the object is at rest. Opposition is called static friction, Fs. I denote it by Fs. We have three options to find the Fs. First, I may believe that Fs is larger than 3. Let's say it's 4. It's impossible. If it is 4, the object will be accelerated leftward, and it's violating my basic supposition. It's at rest. So it can't be 4. Let's say it's 2 newton, less than 3. So the object will accelerate rightward. It's again violating my basic principle here, my basic assumption. Okay, what should I do? There is no way. I should have an opposition 3 newton, which is called Fs in this experiment. So static friction is 3. Let's say I'm pulling the object at a larger force like 5 newton and again the object is at rest. What's your opinion about the Fs? Is it again 3? If it is 3, the object will accelerate rightward. But I told you the object won't move. So here it seems it seems that object is opposed by a larger static friction. That larger static friction must be exactly equal to 5. As you see, static friction is very smart. It can adjust itself exactly according to your force. Not more, not less. What if I pull the object at a force of 8 newton? Anyway, it's the same. Fs is equal to 8. But necessarily it has a limit, Even if the object is very heavy one and maybe very hardly attached to the ground, if you are a very strong person, or if you pull the object with a very huge device like a car, whatever, like a truck, at last the object will move. Okay, let's say this 8 newton is exactly that force that can break this opposition, and the object is going to move after 8. Now this is 8. Fs is now at its limiting value, its borderline. Let's say it's Fs max. It can't be larger than 8 in this experiment, according to the weight of the object and the nature of the surfaces in contact, whatever. Fs cannot be larger than 8 in this experiment. So as you see, Fs has an interval. The minimum value it can have is 0 when you don't pull the object, and maximum value will be 8 newton in this experiment. So Fs is not going to be exactly something, provided you specify the pulling force. If you pull the object at a specific force, yes, you can specifically determine Fs. Otherwise, Fs is leaving in an interval. It will have a value between 0 to 8, according to this experiment. Okay, what happens if I pull the object at a force of maybe 9 newton? Anyway, I believe that I will break this maybe guard, and the object will move. And when the object moves, normally it accelerates. And Fs is not going to be something as an opposition here, because static friction means the object is at rest. What should I call that? Anyway, the previous video I explained everything about dynamic friction. It's going to be dynamic friction, and it's not a friction like Fs anymore. So this 4 newton, it's just an example. It's going to be dynamic friction, and dynamic friction is something that you already learned it in the previous video. I mean in the video 2.10, dynamic friction. Exactly the previous video I already recorded. Anyway, so you learned it. Let's summarize. I have an object, a box at rest, and I pull the object with a force of F, Fs will adjust itself exactly equal and opposite to F. So if I pull the object at a larger force, Fs immediately will be larger, larger, larger and equal to my force. So if I draw a graph like this, here I put the friction, it could be static friction, dynamic friction, whatever. And this is my pulling force, okay? As the object here is at rest during this experiment, this Fs will be always equal to F, okay? So if I increase my force, the Fs will be exactly equal to that. So if it is 3, it's also 3. If it is 4, it's also 4. And you remember in the previous experiment, finally it gets a maximum, the borderline, which is 8, and the object is in threshold of motion. So the static friction will get its maximum, 8. According to previous experiment, anyway, it will have a maximum. So let's continue. Here I call the friction or static friction, and it's always equal to my pulling force, not more, not less. Okay, let's say there is a normal force. Do you know what the normal force is? I previously explained everything about the normal force. You can watch this video. But when the normal force is specified according to weight, according to whatever it is, here the object is, it's on the ground and this is mg and normal force is mg, but it's not always that, you know. So anyway, according to the touch, when the object is in touch with the ground, with a surface, whatever, there must be a normal force. You will specify the normal force and then you can find this Fs max. This Fs max, the maximum value of this static friction, could be determined according to experimental fact by this relation. Fs max is equal to mu s times the normal force. Mu s is called the coefficient of static friction. Mu s has no unit, and it's maybe a unitless coefficient, something larger than 0. Okay, whatever it is, it could be even 1, 1.2, 2, 3. But anyway, it will be given in the question. Actually, it's something that practically you can determine according to the experiment. So if you have the mu s in an experiment, let's say mu s is given to be 0.4, okay? You can determine the maximum static friction. Let's say the normal force in this experiment is 10, okay? So I can say Fs max according to the given values will be mu s 0.4 times 10. So it's 4 Newton. 4 Newton is the maximum static friction. Means that your force could be up to 4 and the object is still at rest. Larger than that, the object will lose its rest status, so it will accelerate, and it's going to be dynamic friction. And you learned dynamic friction in previous video. So the Fs will be always less than mu s times n, or equal to that, and so it's the borderline here. Okay, maximum. Of course, you know that it is exactly the same, mu s times n. Okay, what if I increase my force? Okay, you can increase your force, no problem. Let's say Fs is 8 and then F is 8. I increase the force to 9. This will be all a different thing. It's not Fs anymore. It will be dynamic friction, and dynamic friction will be mu d times normal force. You learned it. So it will be the mu d times n, and the object will accelerate. So if you increase your force, the dynamic friction won't increase. It is always mu d times n. So according to the mu s and mu d, you can determine if the object moves or if the object will keep the rest position. We need some practice, okay? I think it's the time to have some practice. So let's go to a question and then learn it. Before that, values of mu s and mu d could be compared according to different experiments. Normally, mu s is expected to be larger than mu d. Okay, this the given values here, like glass and metal, a couple of surfaces in contact. Mu s is in average is almost 0.7, but mu d, you see, is smaller. So keep in mind and be informed that values of mu(s) are always larger than mu(d). Provided in a question they may suppose that they are equal. Okay, let's start a question. A 2 kilogram mass is pulled by a horizontal force of 8. Look, this is 2 kilogram, a box of 2 kilogram mass, and it's pulled by a force of F. F is 8 here, okay, as shown in figure. Calculate the friction force. When they say friction force, they did not, the question did not specify which type of friction it is. It could be static friction, could be dynamic friction. The person who may decide about it is you. We will decide about the friction, which kind of friction it could be or it would be. What if the force is 12? Okay, let's keep it in refrigerator now. I will consider this part. First of all, let's calculate the friction in this case when F is 8, okay? Here I don't know if the object may move or may be at rest. I have mu(s), which is 0.5 here. So Fs maximum static friction is going to be mu(s) times n. But what the n is expected to be equal to mg. Here mg is 20 newtons because g is given to be 10, so it's 20. And the normal force is expected to be equal to that as it's on a horizontal surface. So n is 20. So here mu(s) is 0.5 and n is 20, so it's 10. According to the given data, I believe that static friction is something between 0 and maximum up to 10. Okay? It's very good because the given force now is 8. It is crazy to have a static friction like 10 here. It can't be 10. The reason, Fs is very smart. It's very smart force. It will adjust itself according to your force. So if you are pulling the object with a force of 8, it will be exactly 8. Why more? Because it's sufficient to hold you. And a static friction has a mission holding the object at rest. It's enough. More than 8, it will accelerate leftward. It's crazy. It's impossible. And less than 8, it will move. So I believe that according to this borderline for the Fs between 0 and 10, the pulling force of 8 will create a static friction of 8. Exactly 8. Not more, not less. So let's consider the question again. Maximum static friction will be mu(s) times normal force mg, and it will be 10. So static friction will be something between 0 and 10. According to your pulling force, it will be adjusted. So if the force is 5, it's 5. If it is 6, let's put 6 here, it will be 6. And now in this question, it is 8. Okay, so Fs is 8. Not more, not less. But it could be up to 10. What if I pull the object with a larger force, like 12? 12 is larger than 10, and it will break this opposition. It will pass the borderline, and Fs is not going to be a valid force here. I should consider the dynamic friction. How? Okay, dynamic friction is always something like mu(d) times normal force. Mu(d) is given to be 0.2, so it's 0.2 times the normal force. Normal force is 20, so it's 20, so it's 4. Done. So if you pull the object with a force of 12, the dynamic friction comes to this scenario, and it will be 4. Is the object accelerating now? Yes, of course it is. The acceleration of the object would be the net force, F net, divided by mass. F net here is your force, which is 12, minus the friction, which is now dynamic friction, 4. So it's 12 minus 4 divided by mass, which is 2. So it's 8 divided by 2 and 4. So the object will accelerate for 4 meters per second square, rightward. If you pull that with a force of 12, but less than 10, no, there is no acceleration, then the object will be at rest. If you noticed, First of all, I try to find the maximum and minimum of the static friction. Then I check my given force, and then I decide about the value of the Fs. Actually, Fs is a smart. It has a borderline, but not always equal to the borderline. It's usually less than that. Okay, let's go to the next question. Look at this question. It's also very instructive. An object of mass 3 kg is pulled by a horizontal force of 9. Look, this is 3 kg. G is given to be 10, 9 Newton. Okay, this 10 is very good for finding the normal force, you know. Okay, let's discuss about it shortly. Horizontal force of 9 as shown in the figure. Calculate the friction force. Okay, friction force means that we don't know if it is dynamic or static friction. We will check. What if we add masses on top? It's also a very interesting question. Add masses on top. Before I go over the last part, let's specify the friction, the static friction. Okay, dear friends, you know that static friction is something always between 0 and a maximum, mu s times the normal force. What the normal force is equal to mg in this question because it's on the ground and there is no vertical force acting on that except mg. mg is going to be 3 times the gravitational acceleration, 10, so it's 30, okay, mu s is 0.5 multiplied by 30, so it's 15. Good. So I know that a static friction is something between 0 and 15 Newton. Okay. My force is not 15. It's less than 15. Okay. So static friction is very smart. It will be a sufficient force just to hold the object at rest. That sufficient force is exactly something we need. How much is it? Good, 9. Not more, not less. Okay, let's keep this force 9. I won't pull the object at any other force, but I will check the static friction according to some additional loads on this object. Let's put some additional masses on top. What happens if I do that? Okay, let's add a 2 kg of mass, an extra load on 3. My force is still 9. Okay, what about the static friction? Okay, let's decide about it. Static friction is going to be something between 0 and again mu s times the normal force. But normal force is different because this package is now for 5 kilograms. So the normal force is 50 mg and mu s is half. So it seems to be 25. So here I see the static friction will be something between 0 and 25. Okay, but how can I decide about Fs now? It's still 9, I think, because this 9 is opposed by exactly 9 Newton of force leftward, because this is very smart to keep it at rest, not more. So what happened when I added a load on 3? Nothing. The maximum friction is increased, but the friction, no. It's very important. So when you have some additional masses on top, although the maximum friction increases, the present value of the static friction is always adjusted by your pulling force. It's smart. It's enough to be 9. Just it guarantees, it has a larger guarantee, let's say. It guarantees up to 25, the object won't move. What if I add another additional mass? Let's say we put another 1 kilogram over. No problem. The total package now has a mass of 6, so it's 60 the mg, and the normal force is 60. Okay, so the static friction will be something between 0 and mu s times 60. Okay, mu s is a half, so it is 0.5 times 60, and the answer will be 30. So maximum friction will be 30 in this experiment. What about the friction? No, the friction will be again the same. This friction is still 9. not more. It is smart, and it's just checking your force. If your force is 9, it's enough to have a 9 newton of opposition, not more, not less, equal to that. But the guarantee of not moving is larger now. So additional masses, additional loads on the object will increase the maximum friction, the borderline of this force, but not the friction. The friction will not be increased. Dynamic friction is different, you know. Dynamic friction is always mu d times the normal force. So about the dynamic friction, if you increase the load, yes, dynamic friction will be always larger and larger. But the condition for dynamic friction is the object is in motion. Here is a very different case. So please keep in mind the static friction has a very, very different nature, and you should determine the value according to your pulling force. And lastly, I should have an additional sentence. Static friction and dynamic friction have their own different coefficients, mu s and mu d. Mu d is always less than mu s. None of them have any unit, but they are specified according to the nature of the surfaces in contact. Thank you very much for watching this video, for being with me. Take care. See you in the next video.